minutes, right? So I have 2 minutes. I can start early to have more time. I have booking.com swag if you want. USB keys, things like that. Do you want me to throw that at you? I can. Here. Also, USB key. Oh, it's a little far. The question slide is not the right one, right? And I even have a bag. Just who wants a bag? Can you pass it behind you? Great, nothing to bring that. Less than I say. Bring that and let's see that. I still have a few seconds. Are some of you already using parallel replication? Yes, some. Okay. Who's using MySQL 5.6? 5.5? Okay. You cannot use parallel replication. 5.7, some people are using 5.7. Okay. MariaDB 5.5. 10.0. 10.1. Oh, there's some people using 10.1. Okay, so I'll start. So my name is Jean-François Gagné. I'm going to talk about parallel replication. So I'm going to talk about MySQL 5.6, MariaDB 10.0, 10.1, and MySQL 5.7. So we'll talk about all the inventory of the current landscape. I'm going to talk about use cases at Booking, and I'm going to also talk what you should try to expect and not to do with those solutions. So Booking.com, just a few words. Some people want to stay in a hotel. All the people who that travel to Brussels are in that situation. And there are some hotels that want to have people to stay at their place. So Booking.com, we're in the middle. We link guests to hotel. So I guess you can read here. We're pretty big. We're worldwide. We have a lot of properties. A number was released some time ago. 21 million bookable rooms on the website. And we use MySQL. The important number here is 85% of those MySQL servers are replicating. So what about the 15 others? Of course, those 15 others are not standalone server. Well, they are standalone server from the point of view of MySQL, but the data is replicated. But I'm gonna come back to this number, to keep that number in mind. This is what we're gonna talk about. And replication, so a quick summary, because it was already discussed today by Renee. Replication, one master, many slaves. The master has the binary log, the journal of all the transactions. The slave downloads the binary log, store that in the relay log. This is the job of the IO thread. And we have the SQL thread that is writing the binary log in the local database. And a slave can produce itself binary log to be itself a master. Replication is asynchronous, so we might have lag. It was single-threaded, now it can be multi-threaded. And it was single master, now it can be multi-master, while I'm multi-source here in MySQL 5.7 and MariaDB 10. So parallel replication, it's relatively new because it's hard. And why is it hard? Because if you run transaction in parallel, you have to be very careful to have data consistency. So you have to make sure that the transaction you run in parallel on the slave gives the same result as what happened when they were run on the master. And if those two transactions touch the same data, well, you might end up not having the same result. So data consistency is the challenge with parallel replication. And why is it important? 10 years ago, 15 years ago, we had server with a single CPU, a single core. Like some of you might remember that. So single-threaded replication was fine there. But today, it's pretty easy to have a server with 12 cores, 24 cores. And it's quite a waste to use a single one of those cores to replicate. Also, the 85% of the server that we're replicating and booking, the 10% other that are not replicating is because we are pushing too much data to those servers. Replication is not keeping up. So hopefully with parallel replication, we will be able to have other solutions for those 15% server and go back to replication. Now the strategy is we write at many places and we have consistency issue. We have to make sure that we write everywhere. But this is a pain. So hopefully parallel replication will alleviate that problem. The other thing why it's important is some resources in computer can give more throughput if you send them many queries. Just think about a RAID 1. There's 2 disks in RAID 1. If you send a single read request, only one of those disks is working. You can serve 2 read requests at the same time with RAID 1. So parallel replication is important. History. I will go through all those solutions one by one, so this is the quick inventory. So MySQL 5.6 introduced parallel replication based on schema. So the concept here is if you have transactions that are schema local, so that only touch a single schema, 2 transactions in different schema do not conflict and you can be running parallel on the slave. So it's a pretty simple idea. It works pretty well, and MySQL 5.6 implements that. So the master tags the transaction with the schema they are touching in the binary log. This goes to the slave, and the slave can dispatch work to many worker threads if they are in different schemas. So if you want to use that, you have nothing to do on the master except having many schemas that you only write to one schema at a time. And on the slave, you set global parallel replication worker to something greater than 0, and you will have many worker threads. So it's as simple as that for MySQL 5.6. MySQL 5.7 has the same behavior by default, and MySQL 5.8 might have a different behavior. So if you want to use that type of parallel replication, you'll have to tell MySQL 5.7 to use the database type. So it looks good, but there's an implication that is really important to understand, is if you run transaction in parallel on the slave based on schema, they might commit in an order that is different from what they appear in the binary logs from the master. So if you have transaction A1, A2, B1, B2, A3, B3 in the binary logs of the master, in this order, A1, A2, A3, so this will be run in parallel with that, and think of that as 2 different workers. And one possible commit order on the slave can be A, B, A, B, A, B. That makes sense. But if B1 is really long to execute, you will have A1, A2, A3, B1, and then the other B2, B3. So, so that is something new, and we have to be aware of that. And there's many other possible different order of commit order. And this is something new, and it has many impacts. First, the impacts of binary logs on slave. 2 different slaves might have different commit order from each other. Maybe one has a warm cache, one is faster than the other. So transactions do not commit on the same order on the 2 slaves. And so the bin logs of those 2 slaves are not, the transactions are not in the same order, and they're different in the master. So Renee talked a little about like doing black magic around bin logs. Well, it becomes increasingly difficult to do black magic around bin logs in that situation. Show slave status will report something, but what will it report? So the position reported by show slave status is a position where everything before is committed, and after, some things might be committed, and some things might be still running, some things might still be queued. So this position here where everything is committed before is called a checkpoint. So show slave status will report the lower watermark where everything is committed before. So we have impact on crash recovery, because crash recovery was taking advantage of this SQL thread position, but the SQL thread position now is more complex, so crash recovery is not as simple as before. It has impact on GTIDs. We can have temporary holes because of the gaps in the transaction execution. And many more. Like if we want to skip a transaction, which transaction will we skip because we are running transaction in parallel? Backups and heartbeat. Like if you're using heartbeat to know what is the delay of your slave, if you have the heartbeat in one schema, the other schema you don't know, so you need to have heartbeat in every schema that you're replicating. So there's some things that we can use in MySQL 5.6 to remove gaps. If you're not using GTID with MySQL 5.6, it might not be crash safe if you're using parallel replication. So it's a very long discussion. Read my blog post from last week about it. For skipping transaction, first remove gaps and go back to single-threaded replication if you want to make sure that you know which transaction you're skipping. And for backups, read the documentation of your backup tool. If you want to know where those gaps are stored, you can go into that table. There's no documentation, there's only the design of parallel replication. It's quite a hard read. And there are 3 tuning parameters for parallel replication. And we'll discuss quickly those. It's all about checkpointing. So I've discussed what is a checkpoint, and checkpoint is tried every slave checkpoint period. So this is a parameter. Every, by default, 300 milliseconds, the SQL thread, the coordinator thread, will try to advance the position of show slave status. But if the next transaction is still running, because it's long, it may be a long outer cable, it will not be able to advance this checkpoint. So checkpointing might, well, fail. That doesn't mean the slave failed. It means that we're not able to advance the position. And you can have some pathetic situation where maybe the checkpoint now is at A1, A2 is reading onto the queue, all the transactions here in another schema are running, but at some point, like the coordinator thread will stop reading ahead and will block because we have a long running transaction here. And so at this point, we will stop executing things in parallel. So the solution is to increase slave checkpoint group, which is the length of the unexecuted transaction, the read ahead where we can have gaps. And if we have big transactions, so imagine a transaction that is 100 megs in the bin log, like this can happen, that will fill the queue of the dispatcher, so you can control that with slave pending job size, increasing that. So that's it for MySQL 5.6. Now we'll go to MariaDB 10.0, and there's 2 types of parallel replication in MariaDB 10.0. Yes?
5.6 is the transactions get executed in different orders, and does it mean that I can have different order increment values?
No, you're protected against that, but the reason is too long to explain now. It's basically, it's in the bin log. The auto increment is in the bin log. But we can talk about that at the community dinner or after the talk. MariaDB 10.0 out of order. It's basically the same idea as 5.6, but instead of using schema-based, MariaDB is using a hint that must be given by the person that is writing to the database. The way to give this hint is to set a session variable which will contain the right domain, which must be independent. So MySQL 5.6, the schemas are independent. MariaDB 10, we have to design the application with independent domain. And the number of threads must be set on the slave. It's also available in MariaDB 10.1, but you can burn your fingers with that, because if you mess up using your right domain, if you think two transactions are not conflicting, but they are, and you advertise them in different right domain, they would run in parallel on the slave, and your data might be inconsistent. So it's more flexible, but it can bite yourself back. MySQL 5.6 has a way to protect you against that. If you do a transaction in two different schemas, it will not run them in parallel. It will block the parallel replication pipeline in the slave, and your data is safe. And we have the same problem, like it's explicitly out of order parallel replication. So we have all the same problem as out of order commit on slave. Gaps, bin log content, show slave status, and all those things. All those things that we discussed with MySQL 5.6 can happen in MariaDB 10.0. A little difference in MySQL 5.6, show slave status is the position where everything is committed. In MariaDB, it's the position of the last committed transaction. So in MySQL 5.6, the gaps are on one side. In MariaDB 10.0, the gaps are in the other side, which can lead to very surprising things. If you stop your SQL thread, you'll see it rewind in the relay log because it must execute its gap. So it's quite surprising. There's a bug open on that. The patch is pushed, so it should be in the next release of MariaDB. If you want the full detail of that, you can use those two references. There's a way to remove gaps. There's a way to skip transaction. And the dispatching algorithm to workers, we'll come back to that after I explain the in-commit order. But there's also special things about long-running transaction and big transaction that we must be careful with. I have time for one question here before we continue. Somebody has a question? So far, so good? Okay. The interesting part. In-order parallel replication in MariaDB 10.0. So the concept here is transactions that are committing together on the master can be executed in parallel on the slave. So if they commit together on the master, they do not conflict. So if they do not conflict, they can be run in parallel. So here we don't need any special design in our database from the developer or different schemas for this to work. Like this works just by itself. So the master, when it will group commit a transaction, it will tag in the bin log a group commit ID, and the slave will read that group commit ID and to be able to execute things in parallel on the slave. So, well, of course, you need the MariaDB 10.0 master, and you set many worker threads on the slave. So now the bin logs looks like this. We have a commit ID at the end here. And so we have one group commit here. We have one group commit here of 5 transactions. So with GTID number 185 to 89. So there's 5 transactions here that have the same group commit ID. They can be run in parallel. We have an orphan transaction here that committed alone on the master. And we have another group here of 7 transactions that can be run in parallel on the slave. So what about the grouping? There's some good grouping and there's some bad grouping. So with sync bin log equal 1, so instead of syncing after every transaction in the master, grouping will happen while the sync is in progress. So while some transactions are being written to the bin log, other transactions are queued. And so this is how MariaDB builds its group commit. If we don't sync, or if we don't sync often, bad grouping can happen because sync doesn't happen, so we don't have time to group transaction. Or if syncs are really fast, if your disk is battery, if there's a cache on your disk and the sync is quick, bad grouping will happen.
What do you mean bad grouping? incorrect grouping or slow grouping?
Small grouping. We will have small groups. So if we have small groups of transactions to run in parallel, we will have very few parallels in proportionality in this step. Thanks, Sean. So there's a way to monitor that using two statuses, binlog commit and binlog group commit. So the number of commits and the number of group commits. And the size of our groups can be computed by a simple division of those two numbers. And we can also optimize grouping. I call this slowing down the master to speed up the slave. So basically, when a transaction is ready to commit, it doesn't commit right now. It waits a little, a certain timeout, for other transactions to join the group. And to make sure we don't wait too long, if there's a decent group size already, once we reach binlog commit wait count, we trigger commit without waiting anymore. So using that, we can optimize our group size and make sure that slave will have transaction to run in parallel. So this is about grouping. Now let's see some things that doesn't work well, and we have to be mindful of that. If we have a very long transaction on the master, so 3 transactions commit together on the master, but one of those transactions is running since a long time. When we run those in parallel on the slave, transaction 2 and 3 are finished really soon. But we have the other one that is a monster transaction that is running for a very long time. So those monster transactions are blocking the replication pipeline. So here, let's suppose this transaction is taking 100 milliseconds, and those transactions are taking 1 millisecond. Running that serially would take, like single-threaded, would take 102 milliseconds. And now in parallel, it's taking 100 milliseconds because we have that monster transaction that is taking all the time. So a message for developer. Before MariaDB, I think 5.3 and before MySQL 5.6, commit was expensive, so it was good to do big transaction. Now it's not anymore. It's not needed to do big transaction anymore because MySQL 5.6 and MariaDB 5.5 and MariaDB 10 do a good job at grouping transactions. And those big transactions become bad in parallel replication, so avoid those. But if you avoid those transactions of 1 second, but 10 milliseconds is still long compared to 1 millisecond. So 10 milliseconds is the time for disk seek. So if you have a transaction that needs to read from disk, it will take 10 milliseconds. If you have a transaction that is in RAM, it will take 1 millisecond. So we're kind of stuck with that. So we'll see the result of some tests. So that was one problem with parallel execution in MariaDB 10.0. Another problem is intermediate master. So if we use intermediate master, and it's quite common, Shlomi talked about it, Rene talked about it, it's quite common in our architecture. Let's see 4 transactions on intermediate master. So on X, 4 transactions commit together. Yay, we have a group size of 4. Those transactions will be executed in parallel on Y. So on Y, those transactions are started together. But the first 2 one commits first, and then the 2 other commits later, because they're not at the same size. So what happened? On Z, they're not running parallel, all the 4 of them. So an intermediate master here will slow down the parallel replication pipeline and will bring problem to second-level slave. I'm talking about how to optimize that, just that. But maybe your question is not about that.
I don't know, my question was why don't intermediate master record the original group?
Well, this is called a binlog server. A binlog server is exactly passing the information of parallelism from the master downstream. So we could think about optimization here, but use binlog server instead. It simplifies everything. And this is not theory. This is not only theory. Like I observed that on the master, if I have group size of 15 and then like 12 in average on the master, on a slave, so an intermediate master that is writing binlog, the group size is going to 5. So we really are losing potential parallel execution on that slave. And that slave was running with 20 threads, so it's not because the slave was running with not enough threads. And I've observed that during my tests. I'll skip that because I have a lot of things to say. Just two things about tuning. Big transaction will be a problem again. And if you use out-of-order parallel replication, make sure that you allocate enough threads to each domain. Slave group commit. This is something really interesting. So we talked about group committing on a master, so putting many transactions at the same time in the bin log. But what about on the slave? Like usually a single threaded slave is running one transaction, begin commit, and then another transaction, begin commit. And those commit here, if you're writing to bin logs, you're writing every time, and you pay the cost of writing to the bin log twice. If those transactions are in different group commit from the master, they cannot be run in parallel. But if they do not conflict, instead of committing T1 right away, we could hold the commit, try to run T2, and then group those transactions together. And so here, we went from 2 writes to the bin log to a single write in the bin log. And not only we did that, we also identified parallelism on a slave. So a slave that ran transaction one after the other was able to identify that those transactions were not conflicting. And I will use that to test parallel replication later. So MariaDB 10.0 does that if you set a number of threads greater than 0, if you set binlog weight, commit weight count greater than 0, and weight usec greater than 0. And also, MariaDB is careful to avoid pathetic weighting if you have conflict, except for DDL. A question about that because it's quite an important concept, so I can answer one question. No questions? Okay. MariaDB 10.1. So MariaDB 10.1 has many types of parallel replication, no parallel replication, only slave group commit, conservative, which was the previous way of doing parallel replication, and 2 new modes, optimistic and aggressive. Aggressive is actually just a more aggressive optimistic mode. So there's something I didn't told you about MySQL 10.0 is even if transactions commit together on the slave, they could conflict. They commit together on the master, they could conflict on the slave. So if T1 and T2 commit together, we could have T2 here because the InnoDB structure is different. We don't have exactly the same pages, the same index. T2 could block T1. And if T2 blocks T1, T1 is not able to complete. T1 is waiting for T2, but T2 is waiting for T1 to commit before committing itself because we have in-order commit. So here we have a deadlock. And to solve this deadlock, MariaDB will kill transaction 2. And you can monitor that with the status. That really doesn't happen often. It really needs a situation where things are really aligned for this to fail. Here I'm running 2,500 transactions per second, and in 4 minutes, I've had 3 of those events. So 3 times for 600,000 transactions. This means 5 times in a million. Okay, this is really something that doesn't happen often. But if it's mishandled, the slave blocks. So we really don't want that, and it's a very good thing that MariaDB kills the second transaction. But here we have a way to run optimistically transaction. So optimistic parallel replication, let's run everything. Let's not care about conflict, run everything. And if there's a conflict, because we commit transaction in order, we will have a deadlock that will be killed. and we will make progress. So this is a natural evolution from MariaDB 10.0, and this is called optimistic parallel replication. So no need for group commit on the master anymore, only for conflict detection on the slave. So to be able to take advantage of that, you need to set either to optimistic or aggressive the slave parallel mode, and of course many threads on the slave. So if you want to know the difference between optimistic and aggressive, read the manual. I don't have time to explain. But there's some things that we cannot roll back. So DDLs we cannot roll back. Transaction in my ISAN we cannot roll back. So those things will block the replication pipeline, because if something conflicts later with those, well, we cannot roll back those transactions. So this is the problem with optimistic parallel replication. MySQL 5.7, basically very similar to MariaDB 10.0. Based on something similar to group commit. It's not exactly group commit ID, it's intervals. We also have a notion of slowing down the master to speed up the slave, and we can have the same problem as with MariaDB 10.0. So long or big transaction will block parallel replication, and intermediate master will slow down parallel replication. Assuming the bin logs, so we have two values in the bin log. It's quite a complex algorithm to explain how this is run in parallel on the slave. In some situations, it could be better than MariaDB. In some situations, it can be worse. Like it's a discussion to have around here. Something to know, though. MySQL 5.7 by default does not commit transaction in order. So we have gaps. And all the things that come with gaps. And we don't have replication crash safety if we're not using GTIDs. There's a parameter to run things in order. It's disabled by default. But to be able to take advantage of that, you need to enable bin logs and log slave update on the slave, which, by the way, in my test are about 10% slower. So I want my slave to go faster. I want to enable parallel replication, but if I want to preserve commit order, I have to pay a penalty of 10%. So that just doesn't make any sense. Please click affect me like Valerie told us we need this to get fixed. And it's still not crash safe. So I don't understand, because there's no gaps. Things are committed in order, but it's not crash safe. So in that situation, show slave status can be trusted. So same thing, it's not crash safe without GTID. If you're interested to run that without GTID, click affect me. I have 7 minutes left to talk about how well it performed. So I did tests for MariaDB 10.0, 10.1, 5.6, 10.0 again. So those are tests. We're not running that at Booking, but this is done in Booking.com environment. Those are real environment. I haven't tested 5.7. 5.7 doesn't have slave group commits, so it's quite hard to do tests with a real-life benchmark without having master in 5.7. So the way I do my test, so for MariaDB 10.0 and 10.1, I have 3 environments, so 3 different master at Booking.com that are production master. They're running MySQL 5.6 as a master here. I put a MariaDB 10.0 slave, a first one and a second one. This one here is slave group committing, so it's identifying parallelism. I need a MariaDB 10.0 master for that, so I'm stuck with B. And then with my last slave, I'm able to run things in parallel. A small comment, details are in the blog post I published about 10 months ago. So group commit, I will skip. A slave group commit has very interesting properties. It can go from not a lot of transactions per second, 50, to much more, but I don't have a lot of time to discuss that if I want to present all the other results. So MariaDB 10.0, my 4 environments. What I do is I'm catching up 24 hours of transactions. So E1 here, in blue, the number of commits per second on that scale, so about 100, 150. And the size of my group on that scale here, so something that varies between 15, sometimes I have 5, but like in average about 10. So this is my first environment. The second environment here, a little less than 100 transactions per second, group size 10, and the two other environments. All the details in the blog post. So the results. So this is speed up with 5, 10, 20, and 40 threads. SB is a slave with binary log, but without log slave update. HD is high durability, so send-in log equal 1 and TRX commit equal 1. So, well, speed ups of little less than 2 for 40 threads. And with no durability, so send-in log equals 0 and TRX commit equal 2. If you're already running with low durability, you can expect speed up of 1.2. This graph is misleading because HD single-threaded is 3 hours and ND is 1 hour. So this is actually much faster, but you do not have good speed ups with low durability. So if I present the result a different way, here is the speed up from HD to ND. This is a speed up of high durability, and if you're already running with low durability, you can expect that. If you're running with high durability and you want to get there, you need to enable both parallel replication and remove durability of your slave. So E1, speed up of a less than 2. A speed up of 1 is the same time to execute. So speed up of 2 is I divide my time by 2 for execution. So E1 and E2, speed up of 2, 2.4. Okay, like this is good. I was expecting a little better, like group size of 10. So I was expecting 4, 5, but my expectations were, I think, high. So I'm a little disappointed here, but hey, it's good. Slave running twice as fast. E3 and E4, like only 30% faster, and here only 50% faster. Well, only, it's still faster, but I cannot take advantage of a lot of cores. So a little disappointed about that, but still useful. I'll skip that. MariaDB 10.1, let's go right now for the aggressive parallel replication result. So here, this is conservative, MariaDB 10.0, MariaDB 10.1, much better. So this is with high durability, so I go to speed up to 2.7. Here, again, with no durability, the speed up are again much better. I had speed up of 1.2, so 20% faster. Now I'm getting more than 1 time faster with speed up of 2. E2, so again, much better. E3 and E4, let's remember, E3 and E4 were bad result with MariaDB 10.0 here, and now they're much better. And this is E4. Do you have a comment on those graphs? How many threads am I using? This is insane. I'm using 1,000 threads. So with 1,000 threads, I'm still getting speed up. I only have 12 cores on those servers. So this is very surprising. The reason is that I'm scheduling IOs in parallel. And because I'm scheduling IOs in parallel, I'm actually doing replication boosting, and I'm prefetching things. Because those are not CPU-bound workloads, those are IO-bound workloads. Those graphs we've seen. MySQL 5.6, good. Speed up to 3.5. This is on a database of a little more than 1 terabyte, 20 schemas, so quite good results. And I'll skip those. This is real world MariaDB 10.0 workload. So, in summary, it's complex to understand. MariaDB 10.0 in order, and probably MySQL 5.7, I'm extrapolating, has limitation around long transaction and intermediate master. So we have to be aware of that. MySQL 5.6 and 5.7 without GTID, not crash safe. MariaDB out of order solution needs careful, I should underline careful, developer involvement. So to me it looks like MySQL 5.6 is a little simpler and safer to understand than MariaDB out of order, which is more flexible but more complex, and you can burn your fingers with it. MariaDB 10.1 aggressive. That's a very good speed up. And all cases, like, please forget big transactions. Long transaction or big transaction you can log. There we go. Some links or reading. And send me a mail if you have questions, or grab me at the community dinner. And I have 1 minute for a question, or 2 questions. Yes?
Just a quick comment on versus aggressive.
Yes.
You didn't have browser.
No, it's optimistic. In the case of slave group init, you'll have the same result as conservative. And because optimistic, the way it works is the master is giving some int to the slave, like do not run those transactions in parallel because they conflict. So this avoids deadlock on the slave and rollback from the slave. So optimistic, this is why it's not aggressive, but I'm not sure about is it better or not. My intuition tells me that it's better, like a rollback is not that expensive compared to an IO. An IO on disk, on a spinning disk, is 10 milliseconds. A rollback is much less than 10 milliseconds. So the conflict is, like the cost of the conflict is less than the gain of prefetching that data in the buffer. But this is an intuition, and that doesn't apply to SSDs. Or it's different with SSDs. Do I have time for another question? Or
Yes.
I have time for another question. This is a question for Fred.
Can I
Yep.
ask one pretty basic question?
Yes.
When you talked about optimistic and pessimistic, is this about performance or is it about actual data durability? You actually, if you have the optimistic model, does it mean sometimes it's...
No, optimistic is correct. Optimistic is consistent. Optimistic is just running transaction optimistically, hoping they do not conflict. And if they conflict, paying the rollback, which will cost CPU. But my intuition here tells me that rollback on spinning this, like getting that data warm in the cache, is very good. In my test, I get up to 25% of rollback. So I'm probably wasting CPU, because I'm rollbacking. But I'm sending more IOs to the disk, and this is why I get speedups.
You get the time for the question, but not for a long answer.
I'm done. Thank you.